We'll be starting applications of derivatives. Uh, this topic is basically the following 4 or 5 things. So basically it's tangents and normals, maxima, minima, maxima, minima.
Hello, sir.
Hello. Increasing, decreasing functions, uh, and then there is Rolle's theorem and Lagrange's theorem. Rolle's theorem plus Lagrange's theorem. So we already know a little bit of each of this, except this you probably already know most of the stuff here. So
Yeah, we did when we started in physics.
yeah, so we will do it a little quickly. It's not very difficult. We'll mostly be practicing questions in this. The point is to be able to solve problems. The theory part is fairly easy. So let's quickly go through what we have to do. The first thing that we'll look at is tangents and normals. So if you have any curve, then this is a point, let's say P, x1, y1, let's say, and this is y is equal to fx, then we know that the derivative actually means the slope of the tangent at this point, right?
Yeah.
So equation of tangent can be written as equation of tangent at P would simply be y minus y1 is equal to dy by dx evaluated at x1 comma y1 multiplied by x minus x1, right?
Yeah.
So that is your equation of tangent, and if at the tangent point you make a line perpendicular to that, that will be your normal. This line will be your normal. This angle has to be 90. This is normal, this is tangent, and the normal equation will come simply by just taking the reciprocal of this,
Slope of
dy
the
by
derivative.
dx x1 comma y1 x minus x1. So that will be your normal equation. Now there are a few terms that you need to know here with regard to the tangent and normal stuff. So what are those terms? Those are subtangent and subnormal, and also length of tangent and length of normal, these things. So if you draw a diagram, if you draw this diagram and drop a perpendicular from this point of tangency to the x-axis, then let's label this as M and let's call it as T and this one as N, this point and this point. So what we call, basically tangent equation cuts the x-axis at T, that is your point T. Tangent normal equation cuts the x-axis at N, that is your N point, and perpendicular from P on the x-axis, that is your M point. Then we call the length PT. PT is this length. PT is called length of tangent, and Tn is called length of normal, and this distance mt is called subtangent, and mn is called subnormal and subtangent. Mn will be your subnormal. Okay,
Sir, I just joined. Can you please explain this part again?
which part?
Like what are we doing right now?
We are doing tangents and normals, application of derivatives, right?
Oh, okay.
The equation of tangent you know how to write, no?
Yes, yes.
This is normal equation, this is tangent equation, and this tangent line cuts the x-axis at a point T, and the normal line cuts the x-axis at a point N. And from the point of tangency, if you drop a perpendicular on the x-axis, that is your point M. Then these are lengths that are defined, and they have like meaning attached to them by definition. So length of tangent will be the distance pt, length of normal will be pn, mt will be called subtangent, and mn will be called subnormal. So now
Okay.
you can actually find all of these things from the tangent and normal equations, right? Because from the
Yes.
tangent and normal equations, you will know that dy by dx at the point x1 comma y1 will be equal to the slope of this line, basically, right? This line.
Yeah.
So that will be equal to this tan theta, right?
Yeah.
This tan theta basically is equal to tan theta. So given a curve, you can find dy by dx, and you know suddenly tan theta here, right?
Yeah.
Right.
And since this is x1 y1 and this is perpendicular, this length is simply y1, right?
Correct.
Yeah. Yeah.
So y1 is known and tan theta is known, then you can find this also and you can find this also, right?
Yeah.
Yeah.
So basically tan theta will be y1 by this. So mt will be y1 by tan theta, right?
Yeah.
So basically mt will be y1 cot theta, right?
Yeah.
And similarly, pt also you can find easily, because y1 by pt will be sine theta, right?
Yeah.
So pt will be y1 by sine theta. pt will be y1 cosec theta, right? So given, if you know your derivative, then you know your tan theta, then you can find all of these things basically.
Yeah.
Right.
Similarly, if this is theta, then this is 90, this is 90 minus theta, and we know that this angle is 90, right? So this is 90 minus theta, right?
Correct.
Correct. So this side is also known, 90 minus theta comes here, so you can now find mn and np, right?
Yeah. Yeah.
Correct.
Correct.
So basically, as long as you know your y1 here, then you can find basically all four lengths,
Yeah. Nice.
right? So you
Yeah.
don't need to remember them. Don't try to remember. Just know the figure. Just know the figure and the meaning,
Yeah.
right? Like there will be formulas given in your book for all of these things. Don't try to memorize these things, because it will be confusing and you might get wrong answers if you make a mistake. Okay. So that is your tangents and normals basically. This figure and understanding how you will find all of these lengths and how you will get this equation. Basically, if you have the equation, you can find point T and point N easily, because you can just put y is equal to 0, right?
Yeah.
Then the point X that comes as a solution of this equation will be giving the coordinates of point T, right? So there are many ways to do this. As long as you understand this figure, it's fine. Everyone got it, no?
Yeah.
Yeah.
Sir, what's like the significance of subtangent and subnormal?
There is no significance. It is just a term that was there before. Like there is no major significance or anything. I mean, there must have been some reason why they were formed initially, the name, but I think it will have something to do with conic sections and all. So I'm not sure right now.
Okay.
But there is no major reason that you need to be aware of. It's just a definition. Maybe in some context, I mean, in the context of differential equations, sometimes you will find these things like the subtangent of a curve is this, then find the curve, things like that. But otherwise, there's no major significance to it. We will move on. We'll move on to increasing and decreasing functions. Increasing and decreasing functions. So what do we mean when we say that a function is increasing on an interval, right? So increasing on an interval means basically if x1 is greater than x2, then implies that f of x1 is greater than f of x2, right?
Yeah.
That is the meaning of increasing. No? As you go forward, it is going up, right?
Yeah.
And decreasing means x1 is greater than x2 implies f of x1 is lesser than f of x2. This is decreasing. So right now, actually, I should have written it with an equal to sign. Okay. So greater than equal to or lesser than equal to. that is increasing, decreasing. If you call it strictly increasing, then you remove the equal to sign.
Yeah. Okay.
So in strictly increasing, you will have to say this.
But then there's an overlap of conditions there, right? In both the cases, in increasing, decreasing, there is both f of x1 equal to f of x2.
That doesn't matter, dude. That is just increasing is a more general definition. It could be strictly or not. Increasing is a more general definition. Strictly increasing in this particular case of that.
No, I mean, we wrote greater than equal to and less than equal to, right? So equal to comes in both of them. So
Equal to comes in both of them.
He's saying
Yeah.
like if fx1 and fx2 is equal to, like they both
Ah.
are equal, then how will we say if it's increasing or decreasing? There's overlap.
If it is always fx1 is equal to fx2, then it will be a
Um,
constant function. No,
Yeah.
constant function is neither increasing nor decreasing.
okay, okay.
That case, it will be neither increasing or decreasing. But we don't have to worry about it. Like in general, the definition is strictly increasing is there is greater, and if you just say increasing, then it means greater than equal to. And you can also define things like non-increasing. Non-increasing means basically decreasing. So it will be the decreasing case. So if someone says non-increasing function, then they mean decreasing. So you will write this condition for non-increasing.
Got it.
And the way to figure this out from derivatives is just think of f dash x greater than 0, right? This is for in an interval. If this is true, then it is an increasing function. And if it is strictly increasing, you remove the equal to sign, right? And
Yeah.
if f dash x is less than 0, it is strictly decreasing. Why is this correct? Because obviously, if slope is greater than 0, then it is an upward type of curve, right?
Yeah. Yeah.
Yeah.
And if slope is less than 0, then it's a downward facing curve, right?
Yeah.
We also have to understand the idea of increasing or decreasing at a point. Increasing or decreasing at a point. So if you have some function, then what will you say? Is the function increasing or decreasing at a particular point? So here we don't have an interval. So you can figure out whether it is increasing or decreasing at a point by checking the sign of the derivative there, right?
Yeah.
Like sometimes derivative might not be possible. Then in that case, what you will say is in the neighborhood of that point, right? Are the neighborhood points above it or are they below it, right?
Yeah.
So you can say that if you have to check at x is equal to a, right? And if you have f of a plus h is greater than f of a and f of a minus h is less than f of a, right? So basically then the graph is somewhat like this, right?
Yeah.
Here a minus h is below, a plus h is above, right? Then it is an increasing graph, right? So this is the meaning for a point. If you want to figure out whether at that point it is increasing or decreasing, you check this. This is increasing. And if it is decreasing, it will be the reverse condition. So f of a plus h should be less than f of a, and f of a minus h should be greater than f of a for it to be decreasing at a point, right? So these are common sense ideas only, nothing very weird. Now, since we know what to do about a point, the interval part is what we discussed earlier, because you have from this point to this point an interval, you check the slope of the derivative in that region, right?
Yeah.
However, notice that this definition does not involve derivatives also, because sometimes you could have a situation like this, right? Non-differentiable, right?
Right, mod function.
Non-differentiable type of functions could be possible, where you have to check it on the basis of just in the neighborhood, right?
Yeah.
So in this case, you will not say it is either increasing or decreasing at this point, because both sides it is below, right?
Yeah. Yeah.
Yeah.
So it is not fitting any of these conditions, right?
Mhm.
It is not going to be increasing or decreasing in that neighborhood. But if it was a mod function like this, right? Okay,
Right.
here also you will not say increasing or decreasing. Actually, it's a point of minima, right?
Yeah.
Mhm.
Correct. So maxima minima is basically not going to fit in the pattern of increasing, decreasing, right?
Mm-hmm.
Because
Yeah.
for maxima minima to happen, the nature should change. It should be increasing to decreasing, something like that.
Correct.
So there is another term that is associated with this, which is called monotonic. So monotonic means if a function is monotonic on an interval, you mean to say that it is either increasing or decreasing, right?
Mhm.
Either increasing or decreasing on an interval, it means monotonic. So the condition for a function to be monotonic is derivative should be throughout either positive or throughout either negative.
Yeah.
This should happen, then it is a monotonic function. Okay. Now, okay. So test for increasing and decreasing we already know. Okay, there are some obvious things that you need to know here. So for example, if f is increasing on an interval, right? F is increasing on an interval a to b and is continuous in that interval, right? Then the maximum and minimum value will be what? Maximum minimum value on this interval will be f of b will be max, right?
Yeah.
And minimum will be f of a,
FFA. Mhm.
right? So this is an obvious statement once you look at it, but sometimes this type of statements are true, but you cannot realize that in a question, like you forget to about that, right? So this is something that you keep in mind, that if you have a function that is monotonic on an interval, maximum minimum values will be at the endpoints, right?
Right. Right.
Okay, so from the increasing and decreasing logic we will get Rolle's theorem. Rolle's theorem basically says that if a function f of x is continuous on an interval a to b and is differentiable in the interior of that interval, differentiable on a to b like this, not on the endpoints. It doesn't have to be differentiable on the endpoints, right? So if you have a situation like this, these endpoints are a and b, how will you check differentiability at an endpoint? Suppose at a, I want you to check differentiability. How would you check differentiability at an endpoint? Hmm? Normal point, you know how to check differentiability, no?
Yeah.
You do what? You do check RHD should be equal to LHD,
Right.
and both should be finite,
Yeah.
right?
Yeah.
At an endpoint, you obviously don't have an LHD here.
Yeah.
Yeah.
So you
So
just check whether
check
RHD
exists
exists
or
and is finite. That's all.
not.
At an endpoint. At this endpoint, you will check whether LHD exists and is finite, right?
Right.
Yeah.
So we are not in Rolle's theorem, we are saying it should be continuous on the entire interval, including the endpoints, and should be differentiable on the interior of that interval, right? Not on the endpoints. It could be non-differentiable here, that's fine. Okay.
Yeah.
Then there exists, there's one more condition, and f of a is equal to f of b, right? Then there exists a c in AB such that f dash c is equal to 0. Okay. So This is Rolle's theorem. So think about why this has to be true. Function is continuous and differentiable, and endpoint values are equal, right?
Right.
Endpoint values are equal. So f of a is here and f of b is here, right?
Yeah. So there will be like either.
Then
or
obviously it has to
or-
turn back, right? Somehow.
Yeah, yeah.
It cannot keep going up, right? It has to come back, right?
Yeah.
Mm-hmm.
Because it is continuous, the graph has to cover whatever values. It cannot be discontinuous graph. You cannot skip values, right?
Yeah.
So it has to turn back. So turning back means that this point slope will be
Yeah,
zero,
slope
slope
is
will be
zero.
zero, slope will be zero, right?
Yeah,
Hmm.
yeah.
There has to be some point where it has to become slope zero, right?
Right.
Because it will start off as increasing, but it has to become decreasing later, or vice versa,
Yeah.
right?
Hmm.
So this theorem is a statement of the fact, it follows from the fact that it is continuous and differentiable, right? Because of continuity, you cannot jump points. You cannot be
Yeah.
like
Hmm.
suddenly here and then suddenly here, right?
Yeah.
And because of differentiability, your f dash x is defined for all points in the interior, right?
Right.
Yeah.
And because fa is equal to fb, it follows that one point must be there where f dash c is equal to 0, right?
Yeah. Yeah.
So there are tricky problems that will come, which will use the fact that Rolle's theorem works. Okay, so we'll see applications where you will have to apply Rolle's theorem on a function between some interval, right? So we will see that. Everyone understands, no, why this has to be true.
Yeah.
Yeah. Yeah.
Okay, so then we look at Lagrange's theorem. Lagrange's theorem, which is very similar to Rolle's theorem. So we'll start off by saying the same thing. Let fx be a function which is continuous on a to b and differentiable in the interior, differentiable on this, right? Now there is no extra condition in Lagrange's theorem. So in Rolle's theorem there was an extra condition of fa is equal to fb, right?
Yeah.
That condition is no longer there in Lagrange's theorem. So basically Lagrange's theorem is a more powerful version of this theorem, right?
Yeah.
It doesn't impose this condition, right?
Hmm.
Then
Yeah.
it says then there is a c in a to b such that f dash c is equal to f of b minus f of a by b minus a. This is the statement. Now we have to try to understand what this means. Okay, so let's draw a graph. It is f of a here. This is a point, so this is f of a, and this point is called a comma f of a, right? And the curve is something like this. Okay,
Hmm.
and this point is b, so this point is called b comma f of b, right? This is the curve. So
Hmm.
what is the statement really saying? That there is a point c in the interval where the slope of the tangent at that c point is equal to the slope of the chord joining the endpoints.
Right. Yeah.
There will be some point somewhere where the tangent is parallel to the chord. Tangent parallel to the chord. What is the chord? Chord is the chord joining endpoints, right?
Hmm.
So
Yeah.
if you look
Yeah.
at the slope of this line joining endpoints, it will clearly be fp minus fa by b minus a, right?
Right.
Hmm.
Yeah.
So we are saying basically there is a point where derivative is equal to the slope of the chord, right?
Yeah.
Slope of the chord. So why is this true? Can you think of the reason why this will be true? I mean, why not? Why are we able to say that? There has to be some reason for that. The previous one, Rolle's theorem, you understood the reason, right? It has to turn back.
Hmm.
Yeah. Yeah.
Yeah.
So here, why is there? Why does this have to happen? Anybody, any thoughts? This is an example that I give to explain this. Last year also I would have told you guys this. So if you are going from, let's say, Bangalore to Chennai, the journey is, let's say, 300 kilometers or 200 kilometers, and you are covering it in 6 hours. What is your average speed? Average speed is
50 kilometer per hour.
50 kilometer per hour. So let's think of this as Bangalore and this as Chennai. So what is this line slope indicate? Like, this is a distance time graph. Okay.
Right.
So this line indicates total
Yeah.
displacement by total time, right?
Yeah.
Yeah, yeah.
So this line slope indicates average speed, right?
Yeah.
Right.
That's instant.
Right. Now, what this theorem is saying is there will be a point in your journey when your instantaneous speed will be equal to 50 kilometer per hour.
Yeah.
Gave it last year.
Yeah. So there will be a point in your journey when you will have to touch 50 kilometer per hour, which was your average speed. Why? Which is now obvious now. Why?
Yeah.
Yeah.
You cannot go through the entire journey at lower than 50, right?
Yeah. Yeah.
Right, right.
Because then your average will not be 50, right?
Yeah.
You cannot go through the entire journey at above 50 kilometer per hour, no?
And
Yeah.
then
Yeah. You can't.
It has to cross, no, then.
Yeah.
Right, yeah.
And since it is a continuous and differentiable function, derivatives are defined at every point, right?
yeah.
Right.
So it has to cross that 50 value. Otherwise, how will it go have average 50, right? So what we are saying is that this portion of the graph here is slower than average speed, right?
Yeah. Yeah.
And this portion of the graph here is faster than average speed.
Yeah.
So then you have to cross the average speed, no, sometime.
Yeah.
You have to cross it at some point because you cannot give slower and reach there, right?
Yeah,
Mm.
yeah.
You cannot be faster always, right?
Yeah.
You understand?
Yes.
Hope this is clear. You
Yeah.
should know the
Yeah.
physical meaning of this and Rolle's theorem. Both of these things should be very clear. And the difference between the two is basically just Rolle's theorem and Lagrange theorem. It says continuous on A to B. It says the same thing. It says differentiable on interior. This also says the same thing. And it says extra condition FA is equal to FB, right? This doesn't say anything like that. And now you are saying that in both cases, in here, you have some point C in that interval, F dash C is 0. And here you say some point C in the interval where F dash C is FB minus FA by B minus A.
Yeah.
Right? So you can say that Rolle's theorem is a special case of Lagrange theorem, right? Because if you put FB is equal to FA in this Lagrange theorem, you'll get Rolle's theorem,
Yeah.
Yeah, yeah.
right? So Rolle's theorem is a specific case of Lagrange theorem, right?
Yeah.
Okay. So one common application of Rolle's theorem is in finding the roots or real roots of a function. Application of Rolle's theorem. So finding the real roots of an equation f of x is equal to 0. So what we can say is, suppose there are 2 points. Suppose there are 2 points A and B such that f of x and f dash x are continuous from A to B. Okay. Suppose there are 2 points where the function as well as its derivative are both continuous in that interval. Okay. And suppose now you have FA and FB have opposite signs, right?
Right.
If FA and FB have opposite signs, then you have to have a point where they cross zero, no? Then
Right, yeah.
Yeah.
one side the function is below x-axis and one side it is above x-axis, right? This is
Yeah.
A
Right,
and this is
right.
B, right? So this is fa is negative and fb is positive. Since fx is continuous, it has to cross this point somewhere.
Yeah, yeah.
So there will be a root C where inside AB, there will be a C in AB such that FC is 0,
Zero.
correct?
Yeah.
So if it has opposite signs, right, then there will be at least one root in AB, right?
Right, right.
Why am I saying at least one root in AB? Because it could cross multiple times, right?
Yeah.
Correct? It could
Yeah.
be like this. It could cross multiple times at multiple places, right?
Yeah, yeah.
So one or more than one roots are possible, but actually odd number of roots are
Odd,
possible,
yeah.
right?
Right.
At least 1 or 3 or 5 or 7, like that, right?
Yeah,
These many roots have to be there in A to B, right?
yeah.
Yeah.
And suppose somebody gave you an additional piece of information that the derivative was never 0 in the interval of A to B, right? If the derivative was never 0 in that interval, then it was always positive or always negative, right?
Yeah, yeah.
Then it would be an increasing or decreasing function, right?
Yeah, yeah.
Then you know that there is only one root
Hmm.
in A to B, right?
Yeah.
Then it cannot be like this, right? Here
Yeah.
derivative is becoming 0, derivative is becoming 0, right?
Yeah.
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 So basically, what are the things that you have to keep in mind? You have to say that there is a function which is continuous from A to B and the derivative is also continuous there, right? If fa and fp have opposite signs, then you know that at least one or odd number of roots must be there between A to B, right?
Yeah,
Right.
yeah.
Yeah.
Because it has to cross once or it could cross 3 times also, right? Or more, right? However, if it is given that f dash x is always positive in that interval or always negative in that interval, right? Basically that f dash x is never 0, right?
Yeah. Yeah.
Then it implies that you will have only one real root in that interval,
Yeah.
right?
Yeah.
Yeah.
Okay. So that is your basic theoretical part, which covers increasing, decreasing, and Rolle's and Lagrange theorem. And then we have maxima and minima. Maxima and minima, which we again already know a lot about. We'll just try to mathematically define each of those things. So, okay, so when do we say that a function attains a maxima or a minima at a point? Attains a maxima or a minima at a point. So when we talk about maxima and minima at a point, we mean local maxima, local minima. We mean to say in that neighborhood, it is the maxima or minima, right?
Right.
So we are not talking about overall maxima minima. If someone means overall maxima or minima, they will say explicitly absolute maxima / minima, right? Absolute, or they will say global. So you are either local or you're global. So right now we are talking about local maxima minima. Most of the time that is what you will be dealing with. If you have found out your local maxima minima, then you can find absolute maxima minima from there by taking the highest maxima and the lowest minima, right?
Yeah.
So there could be multiple points where a function attains local maxima minima. And out of all of these points, you can find which point it is highest and which point it is lowest, right?
Yeah. Yeah.
That will be your global or absolute maxima and minima, correct?
Yeah.
So first what we will understand is what does it mean for a function to attain a local maxima minima at a point. So if it is a local minima, what you can say without doing any derivatives and all, what you can say is in the neighborhood, in the immediate neighborhood of that point, right? Every value limit a f of a plus h should be greater than f of a, and f of a minus h should also be greater than f of a, right? Correct? this will be a local minima, no? Then at f of a. Do you understand what I'm saying?
Yeah, yeah.
In this neighborhood, this value should be above, this value should be above, right?
Right, yeah.
If you want to say local maxima, then you have to say that the neighborhood, immediate neighborhood point should be lower, right? So f of a plus h should be less than f of a, and f of a minus h should be also less than f of a, right? That
Right,
will be
yeah.
a local maxima, right? Correct.
Yeah.
Right.
So that implies, that immediately implies that in this neighborhood, the function should be increasing, and in this neighborhood, the function should be decreasing, right?
Yeah.
And that means that it has changed its behavior from increasing to decreasing, right?
Right.
Yeah.
Increasing to decreasing implies local maxima, and decreasing to increasing to increasing implies local minima, right?
Hmm.
Correct. And we know that increasing means derivative is greater than 0, and decreasing means derivative is lesser than 0, right? So that means from greater than 0 to lesser than 0, it has gone. So derivative has changed sign. So at this point, it should be 0, right?
Right, yeah.
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 And here also derivative was initially less than 0, and now it is greater than 0. So it has changed sign. So derivative should be 0 at this point, right? So that gives us a condition for local maxima or minima. The first condition is that function fx has maxima minima at c, maxima minima at x is equal to c, and if derivative exists,
Mm-hmm.
if f dash c exists, then f dash c must be 0, right? It is possible to for the function to have maxima minima when no derivative exists, right? For example, absolute value function, right, at 0. Correct?
Yeah.
This is not a derivable function at 0, no? It is in non-differentiable here. But it has a minima at 0, right?
Yeah.
Right.
So basically, don't confuse the notion of maxima minima with the existence of derivatives. It's not necessary for a function to have derivatives to be showing local maxima minima, right? So local maxima minima is a more general statement. That's why I said that definition, that neighborhood point should be lower or higher, right?
Yeah. Yeah.
That definition does not involve derivatives, okay? Correct, no?
Yeah. Yeah.
So that is a more general definition where neighborhood points, both sides should be lower or both sides should be higher. Then you will have a maxima or minima, right? But
Yeah,
in
right.
case the derivative exists, then it has to be 0, right?
0.
Correct. So we will define we'll define something called critical points, or sometimes also called stationary points. Critical points or stationary points. So what are critical points? Critical points are basically points where f dash x is 0 if it exists, points where f dash x is equal to 0, right? Also points where it is non-differentiable,
Okay.
where f of x is non-differentiable. Those are also critical points. Okay.
Yeah.
So basically what we will say is that maxima minima can only happen at critical points. Okay.
Yeah.
Maxima minima can only happen at critical points. So critical points you can define in a sentence as those points in the domain of the function, those points in the domain of a function where either f dash does not exist or it is equal to 0, right?
Yeah.
So those points are called critical points. Maxima minima will happen only at critical points, right? Now, if you have a function and if you have to find whether something is a maxima or a minima, right? You have already found your basically critical point. You know it is a point of local maxima or minima, but you don't know whether it is maxima or minima, right?
Right.
Then you have two approaches. One
Mhm.
is the second derivative method. So basically, if you take second derivative, and if the second derivative exists, basically, right? First of all, if the
Mhm.
second derivative exists and is positive, then it is a minima. And if the second derivative exists and is negative, then it is a maxima. And this follows from the understanding that second derivative tells us about the concavity of a curve, tells us about the concavity / convexity of a curve, or the shape of the curve,
Right.
concavity or convexity of the curve. So the shape of the curve, because it is not enough to just know that the function is increasing. So suppose I know that this is my f of a and this is my f of b. We know that you have to join these two, right? But we can join in multiple ways, no?
Yeah.
Yeah.
We can join like this, we can join like this. There are many ways to join, right? So
Right. Yeah.
we need to know the way it is being joined, right?
Yeah.
This type of graph, this curve is called a concave up curve. This
Mhm.
curve is called a concave down curve. Okay.
Sure.
Hmm.
You were telling about critical points, right? So can you tell what the second point was once again?
Either f dash does not exist or f dash is equal to 0.
Okay, thank you, sir.
Those points in the domain where function doesn't have a derivative or where function's derivative, first derivative is 0. Those are critical points.
Mhm.
So
Got it.
right now, shape of the curve. So we are calling this type of curve concave up, this type of curve concave down. How do we distinguish up and down? So think of a nice way to think of it is, think of the cave type of formation, right? So here the cave is up, right?
Right.
Yeah.
I mean, imagine this to be a cave and this cave is upward. So this is concave up and this side, the cave is downward facing, right?
Hmm.
Right?
Yeah.
So the condition for this to happen is f double derivative is greater than 0. And condition for this to happen is double derivative is less than 0. Because double derivative is telling you the shape of the derivative curve, right? Is telling you the slope of the derivative curve, right?
Yeah.
So, I mean, you can think of it like that, or just remember that double derivative greater than 0 or lesser than 0 implies concave up or concave down. Now, if you have a function in some region and here you're expecting a maxima point, right?
Hmm.
Or maxima or minima point, then notice that here the shape of the curve is concave down, no?
Yeah.
Yeah.
Concave down means double derivative is negative, and then this is a maxima, right?
Right.
And if the curve was, see, f dash 0 is 0 at both points, right?
Yeah.
Right.
The
Yeah.
only thing that distinguishes them is the shape of the curve there, right?
Mhm.
If the shape of the curve is like this or concave up, double derivative is greater than 0, then it is a minima, right?
Okay.
And if it is like this, it is a maxima, right? So
Yeah.
that
Yeah.
is one way to figure out whether it is a maxima or a minima. The second way does not employ this. The second way just says with the first derivative values itself, you can figure out. So you can just say that if it is a maxima or a minima, right? If it is a minima here, then slope should be negative before. F dash is negative before and f dash is positive later, right?
Mhm.
Correct. So sometimes, why am I saying this? Because sometimes it might be hard to do another derivative. Like derivatives could be annoying. Like it would be a complicated function where you don't want to do any more derivatives, right?
Right.
So it might be feasible to just check first derivative values just before and just after. You
Mhm.
understand? If it is
Yeah.
negative to positive, then obviously it is a minima. And if it is positive to negative,
Yeah.
it is a maxima, right?
Yeah.
First derivative is positive, then it is negative. So this is a maxima, right? So You can do it by just the first derivative test, or you can use second derivatives. Depending on the function given, you should choose that approach. Right?
Yeah.
Okay.
Right.
There are some, however, some special points, right? There are some special points which are called inflection points. Inflection points, which are special because your first derivative is 0, right? But it doesn't change sign. It does not change sign as expected. Like what I mean is, here first derivative was negative and then it became positive, right?
Yeah.
Correct. So first derivative is actually changing sign, no?
Yeah. Yeah.
But you can find a critical point. Critical point is point where f dash x is 0, where both sides first derivative has same sign, right? You
Okay.
understand? It could be positive this side and positive this side, not in this figure. I will show you. The simple example is y is equal to x cube at 0, right? This is y is equal to x cube. Look at the first derivative. First derivative is 3x squared, which is equal to 0 at x is equal to 0, right?
Yeah.
Right. Yeah.
But it is increasing in this range also and increasing in this range also, right?
Yeah.
Yeah.
So the derivative f dash x is positive here and it is still positive here.
Correct.
So this point is not really a maxima then, right? Or a minima, right?
Yeah. Yeah.
This point is not a maxima minima. Obvious from the figure also that this neighborhood has lower and this neighborhood has higher, right?
Correct.
Yeah.
Right. Yeah.
Right.
So there are some situations where your critical points will not give any maxima minima. That happens when f double derivative is 0, right? Or you can say f dash x does not change sign. Correct? Notice here that double derivative is not positive or negative, as it should happen if it is maxima minima, right?
Yeah.
Yeah.
Double derivative is itself still 0, right?
Yeah.
So then you cannot say, then it is a inflection point. You call it an inflection point where you don't have maxima minima. Okay.
Yeah.
Okay. So that is all that you need to know about maxima minima. Now basically it's about practicing problems and solving problems and getting comfortable with all of these ideas. Okay. So we will look at some questions now. Most of this theory here you already sort of knew. So we will start doing some questions and we'll see if we are able to get the answers. So the first question is, if let f be a 3 times differentiable function, it is defined on R and is real valued. Basically its range is also real. Real valued function such that f has at least 5 distinct real roots. Okay. Then what can you say? Which option is correct? Basically, what can you say for the roots of h of x is equal to f of x plus 6 f dash x plus 12 f double dash x plus 8 f triple dash x. The options are these. H of x has no real roots. Second one is h of x has at least 2 real roots. Third one is h of x has at most 2 real roots. And fourth one is none of these. So we will use the concepts in this chapter to try to figure out this one. Okay. So think about it for a couple of minutes. Try to think what you can do here. So here you have to use the idea that if your function, look at a quadratic graph, right? Quadratic graph is like this, no? This is a quadratic function, right?
Right. Yeah.
Yes.
If you have two roots here, right? Two real roots of this quadratic, then between any two real roots of the quadratic, there will be one real root of its derivative, right?
Yeah.
Yeah.
Correct.
At one point between any two real roots of the quadratic, right? Correct. So
Yeah.
if you have a continuous and differentiable function between any two roots of f of x, there will be one root of f dash x.
Right.
Okay.
Yeah.
Yeah.
So that will be used here. So this type of questions are basically slightly tricky ones where you have to imagine a function, where you have to imagine a new function and apply concepts on those new functions. So I will just show you what has to happen here. Let's imagine a new function g of x. Okay, let's say g of x is equal to e power x by 2 f of x. Let's say for now you have to suspend your intuition in the sense that, like, how can I think of this, right? So you have to ignore that thought right now. Just see how it works, and then we'll see how it could not have worked also if you had chosen something else, right? So so if g of x is this, and now what is given to you? What is given is that f has at least 5 distinct real roots, right? So that implies that g of x also has 5 distinct, at least, right? At least
Yeah.
5 real roots, because g of x is just multiplication of this, and this is positive always, right?
Yeah. Yeah.
So say whenever fx is 0, gx is 0, right?
Yeah.
Okay. So now g of x is a function that is continuous and differentiable as long as f of x is differentiable, right? Because this part is totally continuous and differentiable everywhere, right?
Yeah.
Right.
Yeah.
Right. So then we can say between any two roots of g of x, there is one root of f of x, g dash x, right?
Yeah.
Correct. So if g of x has 5, then g dash x will have 4, right? At least 4 real roots, right? Because
Correct.
when a quadratic is there, at least one real root will be there for the linear function, which will be the derivative, right?
Yeah.
Correct.
Because
Yeah.
g dash x has degree, whatever is the situation, there will be 4 at least, no?
Yeah.
Because
Yeah,
you will mark 5 points like this, right? One here, one here, one here, one here, right? For
Right.
g dash x. And double dash will have at least 3,
Yeah.
and triple dash will have
Triple
at
dash
least
will have
2.
to.
You cannot do anything beyond triple dash because we know f dash x is only 3 times differentiable, right?
Yeah.
At least 2 for triple dash x, right? After that, I don't know whether it is possible to take fourth derivative or not. right?
Yeah.
So I will just stop here and I'll say G triple dash X has at least 2 real roots, right?
Yeah.
So now let's calculate our Gx is e power x by 2 fx. So let's calculate G double dash x, single dash. So it will be e power x by 2 into half fx plus e power x by 2 f dash x, right?
Yeah.
Correct?
Correct.
Double
Yeah.
derivative, let's do that also. Half into e power x by 2 into f of x plus half into e power x by 2 into f dash x plus half into e power x by 2 into f dash x plus e power x by 2 into f double dash x, right?
Yeah.
So notice this becomes what? This part is here and this part is not there anywhere else. Okay. So it is 1 by 4 e power x by 2 f of x plus what is this? This part is common here and here, right? So it is
Right, yeah.
e power x by 2 f dash x plus e power x by 2 f double dash x, right?
Right.
And now this is your double derivative. One more step you have to do. One more derivative you have to do, which will be annoying, but you have to do it. So this will split into 2, this will split into 2, this will split into 2, right? So you'll have 1 by 4 into 1 by 2 e power x by 2 f of x plus 1 by 4 e power x by 2 f dash x, right?
Yeah.
Plus 1 by 2 e power x by 2 f dash x plus e power x by 2 f double dash x, right? Plus 1 by 2 e power x by 2 f double dash x plus e power x by 2 f triple dash x, right?
Yeah.
This is your derivative of g triple dash x. I'll write it properly here. G triple dash x is equal to, let's calculate all the terms that are common types. So this term is alone. So it is 1 by 8 e power x by 2 f of x, right? Plus single derivative terms are there here, right? So 1 by 4 plus 1 by 2, right? So that is going to be 3 by 4, right?
Yeah.
3 by
Right.
4 e power x by 2 f single derivative plus double derivative terms are here and here. So that will become 1 plus 1 by 2. So 3 by 2, 3 by 2 e power x by 2 double derivative. And finally, e power x by 2 triple derivative, right? Correct. Correct, no?
Yeah.
So this function, now take e power x by 2 outside by 8 outside, right? What do you get? F of x plus 6 times f dash x, right? Plus 12 times f double dash x, right? Plus 8 times f triple dash x, right? So g triple dash x is becoming this thing, right? Correct. Correct, no?
Yeah.
And we had earlier said that g triple dash x has at least 2 real roots, right? Correct?
Correct.
Because g of x has 5 at least, no? That's why.
Yeah. Yeah.
4, 3, 2, right? So now this part is always positive, right?
Yeah.
So we know that
Yes.
this has at least 2 real roots.
Correct.
You understand? And
Yeah.
that is the question. Look at the question now, right? This is your h of x, no?
Right.
Yeah, yeah.
So it would not have worked if you had picked any other function. If you have picked e power x, no, it will not come this 8, 6, 12, 8 and all. If you pick anything else also, no, it will not come. So this is the definition of a trick question, where only if you know what to pick, or if you guess the right function to pick, you will get derivatives with these coefficients, right?
So then how do you solve these kind of questions? Like you
Have
just
enough
to guess, or-
experience. Yeah, have to solve enough questions to be able to guess.
Like function equation.
Yeah, there is no rule. Okay, so there is no rule. You just have to have enough practice and you have to see enough cases to be able to guess. Like, there's nothing that I can say here other than have enough experience. Okay, so we were able to deduce what you can say about hx, which is a function of the roots of f, derivatives of f, right?
Yeah.
So because the condition that we are using, the theory that we are using is between any two roots of g, you will have one root of g dash.
Mm,
And that can be extended to double derivatives, triple derivatives, and so on, right?
yeah.
Right.
But beyond that point, this was just a matter of knowing what to guess. Okay,
Right.
so this type of thing can happen. Let's move on, it's fine. Question 2. Question 2 says find the minimum value. This will be in your Allen book somewhere. Find the minimum value of mod of sin x plus cos x plus tan x plus cot x plus sec x plus cosec x mod for all real numbers. Okay,
Mhm.
this is your function. You have to find minimum value of this. Now obviously you cannot apply AMGM. Okay,
Yeah.
you can't, because sine and cos can be negative, right? These things,
Correct.
if they were always positive, you were in, if it was only in the first quadrant, all the angles were in the first quadrant, then I would have just said greater than equal to 2 plus 2 plus 2, right? Because I will group sine and cosec together, cos and sec together, and tan and cot together.
Mhm.
Right, right.
Yeah.
And I will say that they are reciprocal quantities and it is all positive stuff. So it will be greater than 2, 2, 2, right?
Yeah.
But the question is for all real x. So then now it is not easy. Now you have to do some stuff. So you have to try and simplify this function in an intelligent way. Before you do the
all sine and cos, right?
what?
We can start with making all sine and cos.
Correct. That is the starting point. Sin x plus cos x plus tan plus cot will be on top, will come cos square plus sine square, right? So it will be 1 by sin x cos x,
Yeah.
right? And this one will be sin x plus cos x by sin x cos x, right? Right now I'm not worrying about the mod. I'm taking out the inside part and I'm thinking of that function, right?
Right.
Right.
So sin x plus cos x can be easily written as root 2 cos of pi by 4 minus x,
Mm-hmm.
right? Because you can multiply and divide by root 2 up and down, right? And
Yeah.
it will be 1 by root 2, and this can be written like this. So okay, so this part I know what to do, and I can write this part as half sine 2x, right? Correct?
Mm,
Sin x cos x.
yeah.
Right.
Right.
Yeah.
So
Denominator.
so now what I will say is maybe take another angle y is equal to pi by 4 minus x to make it a little simpler. I don't want to keep writing this. So then I will say that this thing is becoming root 2 cos y plus 1 by half sine 2x, right? So what is 2x here? X is equal to pi by 4 minus y, right?
Yeah.
So
Yeah.
2x is equal to pi by 2 minus 2y, right? Correct?
Mhm.
So sine 2x will be sine of pi by 2 minus 2y, which will be cos 2y, right?
Yeah.
Correct?
Yeah.
Sine 2x will be sine of this thing. So it will be cos 2y. So I can write 1 by half cos 2y, right? Plus on top sin x plus cos x will be root 2 cos y by sin x cos x will be half cos 2y, right?
Yeah.
Correct. Okay.
Correct.
So what we are getting is root 2 cos y plus 2 by cos 2y plus this part becomes 2 root 2 cos y by cos 2y, right? Correct.
Yeah.
Yeah.
Correct.
Okay. Fine. Okay, okay. Great. So now I have to think about maximizing this thing, right? Minimizing this thing, right?
Mm.
Okay, so everyone has written down this part.
Yeah, yeah.
What have I done? I have done this substitution to
Yeah.
make it a little simpler to look at least.
Hmm.
So I got this. Now I will just write root 2 cos y plus, what was it? 2 by cos y, right? Cos 2y. 2 by cos 2y, right? The second term. Plus it was 2 root 2 cos y by cos 2y, right? Correct.
Right.
This is what it was, no? Yeah, this was.
Yeah.
Yes, yes.
So cos 2y I know is 2 cos square y minus 1, right?
Yeah.
So we can say that that is root 2 cos y whole square minus 1, right?
Hmm.
Correct. So the whole thing can be written in terms of this variable of root 2 cos y, right? We can write it as root 2 cos y whole square minus 1 plus 2 root 2 cos y by root 2 cos y whole square minus 1, right?
Yeah.
So if I take root 2 cos y as my t, right, as a new variable, right? And I can say t plus 2 by t square minus 1 plus 2t by t square minus 1, right?
Right,
Yeah.
yeah.
Correct?
Yeah.
And the t
Yeah.
goes from minus root 2 to root 2, right?
Yeah.
T varies from minus root 2 to root 2, right?
Right,
So
right.
my function is becoming this thing. So maybe we can simplify it a little bit. Let's try and simplify it. It is becoming 2 1 plus t by t square minus 1, right? That is 2 by t minus 1, right? So the function is simply t plus 2 by t minus 1, right?
Yeah.
Correct. Right?
Yeah.
Now it is very easy to differentiate and find minima maxima. It is differentiation is 1 minus 2 by t minus 1 whole square, right?
Yeah.
So this is 0 if 1 is equal to 2 by t minus 1 whole square, right? So t minus 1 whole square is equal to 2. So t minus 1 could be plus minus root 2. So t could be 1 plus minus root 2, right?
Yeah.
Correct. And t varies from minus root 2 to root 2. So you cannot be 1 plus root 2, right?
Yeah.
Yeah, yeah.
It cannot be 1 plus root 2. It has to be 1 minus root 2, right? So
Yes.
at that particular value, if you put it in this function, you get 1 minus root 2 plus 2 by 1 minus root 2 minus 1. So minus root 2, correct?
Yeah.
So you get 1 minus 2 root 2, right?
Yeah.
Yeah.
Correct. So now absolute value of this thing is simply 2 root 2 minus 1.
Correct.
Ultimately, you have to take absolute value, right?
Yeah.
Yes.
So the absolute value, the minimum value of my function sin x plus cos x plus sec x plus tan x plus cot x plus cosec x is equal to greater than equal to 2 root 2 minus 1. Okay.
I got
So
it.
which is basically approximately 1.828, right? So notice that if it was positive range, right? If it was first quadrant angles, it was greater than equal to 6. But if it is not first quadrant angles, it can be much lesser, right?
Yeah.
You understand?
Right,
Yeah.
right, yeah.
Okay.
Yes.
So how did we do this question? We did not just start off and started differentiating immediately, right? Because that would have made it really complicated. If you had tried differentiating from the beginning itself, no, it would have become really annoying. You would not have been able to solve the equation f dash x is equal to 0 immediately. You understand? Because all of the
Yeah,
things would have been trigonometric and many weird things would have happened, right?
Right.
So what we did first was simplified and made it in terms of sine cos and got it as some sin x cos x and all, right? Then we thought of some good substitutions. So one thing that we did was pi by 4 minus x we took as y, right? That
Yeah.
helped us a lot because it became cos y cos 2y, and after that one more substitution we did, which was root 2 cos y is equal to t, and then it became an easy function. We just have to be careful that whenever we do a substitution, your new variable will have different range, right? So you have to be careful. Like I did root 2 cos y is equal to t, right? So this one can only take values from minus root 2 to plus root 2. So basically your t can only take these values, right? You understand what I'm saying? Every
Yeah,
time you
yeah.
change variables, you have to be a little careful of what are the possible values that your new variable can take, right?
Right.
New
Yeah.
variable cannot be anything that you want,
Mhm.
right? Okay. The next question is this. Tangent at any point on the curve x is equal to a cos cube theta, y is equal to a sine cube theta, meets the axis in P and Q. Okay, the locus of midpoint of PQ. Midpoint of PQ. So many types of coordinate equation type questions can be asked, but they are solved by derivatives, applications of derivatives. So this is a question where it is sort of like a coordinate question, right?
Correct.
Tangent at any point of this curve is defined in terms of these parametric equations. So your x and y are defined in terms of a parameter theta.
Yeah.
Okay. At any point of the curve, the tangent meets the axis in P and Q. So basically, if your curve is something like this, your tangent here will meet the axis at here and here, right? You will call the x-axis point P and the y-axis point Q.
Right.
You have to find locus of midpoint of PQ. So basically, just write tangent equation. It should be fine after that, right?
Yeah.
Because if you know the tangent equation at any arbitrary point here, then you can find P and Q easily in terms of that point theta.
Hmm.
So what do you need to be able to write tangent equation? You need slope, right?
Okay.
Yeah. Yeah.
You need dy by dx, you need, right?
Yeah. Yeah.
So how will you find dy by dx here? If it is like this, right?
Parametric. Parametric.
So do it like this, dy by d theta by dx by d theta, right?
Yeah.
Dy by dx can be defined by first taking derivative here and derivative here and dividing those two derivatives.
Yeah.
Okay. So if you do dy by d theta, you will get basically 3a sine square theta cos theta, right?
Yeah.
And if you do dx by d theta, you will get
Minus 3a.
3a cos square theta minus sine theta, right? Correct.
Yeah.
Correct.
Yeah.
So dy by dx would be the ratio of these two. So what you will get is minus tan theta,
Yeah. Yeah.
right? Minus tan theta is coming.
Hmm.
So my equation of the tangent is y minus y1, and y1 is the point theta here. So y minus a sine cube theta is equal to minus tan theta slope into x minus a cos cube theta, right?
Right. Yeah.
This is your tangent equation. So you could simplify it a little bit. Let's try that. Okay. So you can write it as y minus a sine cube theta is equal to minus sine theta by cos theta, right? And divide this side by the sine theta and keep the cos theta here, right? You
Yeah.
get y by sine theta minus a sine square theta is equal to minus x by cos theta minus a cos square theta, right? correct?
Right. Yeah.
So this becomes y by sine theta plus x by cos theta is equal to a, right?
Hmm.
Right? See,
Yeah. Just
because this goes that side,
yeah.
right?
Yeah.
So
Yeah.
your equation is basically x by a cos theta plus y by a sine theta is equal to 1, right?
1. Yeah.
And this is in the intercept form of straight line.
Hmm. Hmm.
You remember x by a plus y by b is 1. It's in intercept form.
Oh
Yeah.
yeah.
So your P point and Q point are immediately a cos theta comma 0 and 0 comma a sine theta.
Yes.
Right?
Right.
P and Q, right?
Yeah.
So midpoint is now easy and locus is easy, right?
Mm-hmm.
Locus
Yeah.
of midpoint will be h is equal to a by 2 cos theta and k is equal to a by 2 sine theta, right? And
Yeah.
locus will be coming if you do 2h by a whole square plus 2k by a whole square is equal to 1, right?
Yeah.
So locus equation will be x square by a square plus y square by a square is equal to 1 by 4, right? So it's a
Yeah,
circle actually. X square plus y square is equal to a square by 4, right?
Yeah.
That is your locus. So whenever there is a tangent normal type of equation, the questions will be more or less easy. You just need to follow your logic of coordinate geometry, right?
Yeah.
And apply a little bit of derivatives here to get the slope and all, right?
Mm-hmm.
Okay. So we will stop at this point and we will next class onwards will be practice problems of this chapter. So we'll do more questions, at least 2-3 classes we will do on
Next,
application of
physics,
derivatives. Our next 2 classes will be physics.
Okay.
Do you have the Allen booklet for AOD?
Yeah, we have
Yeah.
for all the chapters.
Yeah.
The last chapter
Okay,
that
so
starts in.
okay. So you should actually be beginning to work on your limit continuity and differentiability and derivatives and all. Okay. So
Yeah.
you should work on your beginner boxes and whatnot and basic exercises. You can ask those in the next few classes of maths, right?
Yeah. Yeah.
Start doing that so that you can fix your doubts and all everything in the next couple of classes, right?
Yeah.
Sure, sir.
Okay. So next class will be on Thursday and Friday. We had decided, or Friday and Saturday.
Friday and Saturday.
Right.
Okay. Friday, Saturday mornings. Okay.
Yeah.
That will be physics. We will continue with what we were doing.
Yeah.
Okay. That's all for now.
Thank you, sir.
Bye.
So,
Bye, sir.
Bye, sir.